First of all, good afternoon, everyone, and thank you all for joining in and listening into this talk on radon. The title of the talk is Radon in Workplaces, Practical Implications of the Proposed New IAEA Guidelines. My aim today is to give you an overview of this upcoming document, and I was involved in its production, and it's soon likely to be part of the IAEA Specific Safety Guide series of documents. I will say that radon is a rather large topic, so I won't be covering all of radon, but I'll be looking at particular areas rather than trying to cram everything in. Still, even when I reviewed this presentation just before this morning, I did realise I've had to cover a lot of ground. I am going to turn my video off. I hope you don't mind. Part of that is to save on bandwidth, but you should still see everything. The talk today will be in three main parts. Firstly, a quick introduction to radon and discussion on some of the important concepts. Apologies to those who know the basics, but it's always a good place, good way to start and set the scene. I would then like to provide an overview of the content of the upcoming document and the requirements that it might contain. Then I would like to cover a couple of practical implications from the document, including a couple of surprises for me, even though I was on the working group. And then I'll provide some closing comments. I will say that this talk builds on the talk that I gave at ARPS earlier in the year in Canberra. Just before I start, let me clarify. In this talk, I will be referring to both Radon 222, which is generally referred to as radon, and Radon 220, or 220, which is commonly called Thoron. I will try to use the term radon for aspects that apply to both isotopes, and the terms radon 222 and 220 for the respective isotopes. But please forgive me if I mess this up. Also, this talk is not about radon in homes or environmental radon, both of which could be topics for future talks. The IAEA has already produced a document on indoor radon and radon in relation to the public. The focus of this talk is on occupational exposure to radon and radon at work. Now, let me say those two terms again. The focus of this talk is on occupational exposure to radon and radon exposure at work. They're slightly different terms. Occupational exposure refers to work-related sources of radon in the workplace that results in exposure. For example, working at a mineral sands operation or in a laboratory that uses a radium solution. Radon exposure at work refers to naturally occurring radon that might exist in elevated concentrations in the workplace. For example, a basement made of granite or in granite or a cave. That slight distinction is actually quite important, and I'll refer to that a bit later. So let's start at the beginning. There is an increasing focus on radon as a significant potential or an actual workplace hazard. A quick look at the internet and you can be flooded with lots of alarming statements, particularly from Europe, the US and Canada. As you can see there, radon is the #1 environmental cause of cancer deaths and the #2 cause of lung cancer deaths. There's also a quote from the UK Health Security Agency that says, in workplaces such as offices, where hazards are normally low, radon can be the largest occupational health risk. There are statistics available, and this slide shows some of those statistics, and I apologise for them being UK statistics. But this graph refers to radon at home, not work, so I'll just make that known, but gives an idea of the magnitude of the radon hazard. Most of the work on radon comes from the Northern Hemisphere, of course, from Europe, Canada, and the US. But you can see here that lung cancer from smoking resulted in about 28,000 premature deaths per year in the UK, whereas lung cancer from radon exposure at home resulted in 1,000 premature deaths in the UK. So I'm just going to go back a slide and just reflect on the statements. Radon is the #1 environmental cause of cancer deaths and the #2 cause of lung cancer deaths. I suppose I look at that and think that they may be alarming, but that's a personal opinion. In Australia, radon concentrations are generally low compared to the rest of the world. And this is a graph from the ARPS website, which has geometric mean indoor radon concentrations on the left hand, on the y-axis, I should say, sorry, on the y-axis, and country on the x-axis. You can see that Australia generally has low average radon concentrations to many places in the world. However, there are many workplaces such as mines and mineral sands operations where elevated concentrations of radon are present. ARPS also identifies a number of places where elevated radon may be present. For example, highly energy efficient buildings in areas of high radon potential, underground workplaces, or workplaces with elevated radon concentrations, such as spas using natural spring waters, or enclosed workstations or workplaces with limited ventilation. Concentrations are elevated around mining projects in Australia, and there's lots of free, I should say, publicly available information in environmental impact statements and in environmental effect statement reports, which are generally available online. And just quickly, there are results from some of the uranium miners and the rare earth projects. For example, Nolan's project in outback Australia has an average of about 40 becquerels per cubic metre across the region. The Olympic Dam area has an average of about 20 becquerels per cubic metre. And in Western Australia, around the centipede deposits north of Kalgoorlie, the radon concentrations can vary from 10 to 70 becquerels per cubic metre. So we do have wide variability across the country when we think about workplaces. In Australia, ARPS recommends the following reference levels. And reference level is that level above which you need to do something. So for households, it's 200 becks per cubic metre, and for workplaces, it's 1,000 becquerels per cubic metre. PANZA has, I will note though that the reference levels in many European workplaces are a lot lower than the Australian standards. It's also worthy to note that despite EU standards, the countries tend to do their own thing. So you have reference levels for workplaces varying from 300 becks per cubic metre to 600, and in some places 1,000. So it always surprises me looking at Europe and thinking that there's a common approach to stuff. There's not. Interestingly, as a rule of thumb, 1,000 becquerels per cubic metre for continuous workplace exposure using default equilibrium factors gives you about 10 millisieverts per year. Sorry. In Technical Report 161, PANZA also conducted some passive radon surveys in underground mines, not uranium mines, but general underground mines in Australia, and the results were published in that report. And you can see that some of the radon levels are quite high. So considering that the underground mine is a workplace, you can see that there are levels above 1,000 becks per cubic metre in some cases, but also above what the Europeans would look at, which would be the 300 becquerels per cubic metre as well. So it does indicate that there might be something we may need to look at. Okay, let's go. Big rewind back to year 10 physics, or if not year 8 physics, and just have a quick look at some radon basics, and also some, in the next couple of slides, some radon not so basics. So firstly, where does the radon come from? Well, everywhere we have 3 naturally occurring decay chains: the U-238 decay chain, U-235 decay chain, and the Thoron-232 decay chain. Each of those decay chains has a radon isotope. In the uranium decay chain, we have radon-222, which we generally call radon. On the right-hand side, in the thorium 232 decay chain, we have radon 220, which we generally call Thoron. In the middle, in the U235 decay chain, there's also radon 219, which I think is called actinon, and that is generally quite low in concentration in the atmosphere. Oops. So as Pup mentioned, radon is an inert gas, and when created, it will start to diffuse through its host material. If it's able to reach the atmosphere, then it becomes airborne and can move. I tend to think of radon as a bit of a bus. It moves radionuclides from one fixed location to another location. In the most common radon 222 is the most common isotope, and it's from the U238 decay chain and is produced from radium 226. The radioactive decay of radon 222 has a half-life of 3.8 days and produces a number of short-lived decay products. The short-lived decay products are solid particles and can attach to aerosols in the air, or they can remain unattached. Remember, as unattached, they're charged as well, so they're looking to stick to something. Now, the important thing is the half-life of radon gives us two important bits of information. Firstly, how quickly or how slowly the radon itself decays. And secondly, how quickly it will grow in from its parent radium 226. You will remember that the activity of a decay product grows in with its own half-life. And this is important. This will be important later when I talk about Thoron. The main exposure pathway from radon is obviously inhalation, but there's also a secondary exposure pathway, which is dissolution of radon 222 in groundwater and the possibility for ingestion. Although the major exposure pathway is usually turbulent water flows resulting in the release of that radon, for example, in water treatment plants. Oops. The decay products can be seen here. We know that alpha particles do not have a large penetrating depth, but do have high ionization density and can impact on cell linings of the lung. As previously mentioned, the half-life of a radionuclide tells us how quickly it will grow in, and the decay products of radon 222 have very short half-lives, which means the decay products grow in very quickly and decay very quickly. This means that there can be a relatively large amount of energy delivered in a short time before the decay products are removed from the lungs. This picture shows how the decay products grow in. And on the y-axis, we have becquerels of radon. On the x-axis, we have time. An interesting aspect of this diagram is that it shows two mechanisms of potential radon buildup, and there are hints at controlling that. So the first buildup is the radon itself, which is continuing to decay. And the second thing is how long the radon remains in the air. The longer the radon is in the air, the more ingrowth of decay products occur. So ventilation, when you talk about ventilation as a controlling mechanism for radon and radon decay products, you need to think about both. It is important that time is one of the factors when it comes in to controlling radon and its decay products. While we talk about risks and impacts from radon, it is important to remember that only about 1% of the dose to the lung comes from radon itself, or radon 222 itself. This is because most of the inhaled gas is breathed out again. With a half-life of 3.5 days, the probability of radon decaying in the lungs is very, very low. The dose arises most entirely from the short-lived radon decay products, the atoms of which attach themselves to dust particles in the air. These particles, as well as the unattached particles, can deposit in the lung and deposit their energy as well. For radon, the units are becquerels per cubic meter, which means activity of radon per unit volume of air. For radon decay products, the units are joules per cubic meter, usually microjoules or nanojoules, which is the amount of energy in the air. There are many measurement techniques for radon, some good, some bad. And again, this could be the subject of an entire lecture. There are also many instruments on the market, many instruments. And my advice when looking at instrumentation is to know exactly what you want to measure before you buy. And that includes resolution, it includes sampling time, it includes a whole lot of factors. There are many different devices. Okay, I'm going to increase the level of complexity here. Hopefully you're all still with me. The radon concentration and radon decay product concentrations is related through the equilibrium factor. This is an often overlooked and undervalued parameter in my mind, but it's really easy to measure. It's an important factor when estimating impacts from radon alone. The relationship is shown there, dot point 1, 2, 3, 4. When the equilibrium factor is 1 becquerel per cubic meter of radon will equal 5.56 by 10 to the minus 6 microjoules per cubic meter. There are default equilibrium factors, usually based on lots of sampling. UNSCEAR recommends 0.4 for indoor and 0.6 for outdoor. And our PANSA recommends 0.4 or a measured result, brackets, with regular checking. And I just want to reiterate the importance of the equilibrium factor. For example, if I'm estimating the dose impacts of radon in a proposed workplace, and remember, I'm not measuring because I'm estimating what the dose might be, I need to do some modelling. You can estimate the emissions into the workplace air of the radon gas based on emanation rates or some standard emission factors. And then maybe using a box model or some Gaussian plume model or some other ventilation model, you can then determine what the equilibrium radon concentration is. Once you've determined what the equilibrium radon concentration is, you can then use the equilibrium factor and the factors there to estimate a radon decay product concentration. And from that, you can estimate a potential dose. So there is value in understanding what the equilibrium factor is, particularly when modelling is in place. So here are some actual measurements. Concentration of radon and radon decay products can be highly variable depending upon many different factors. And in this case, the picture on the left shows diurnal variation over the period of about a month. At night, the radon concentrations go up and the radon decay product concentrations go up because of the stability in the atmosphere. And this could be any surface workplace, any factory. It could be a mine site. It could be anywhere. These sort of results occur in any sort of surface workplace. To the right is a summary graph of some monthly average equilibrium factor data. And you can also see that that's highly variable. So that both of these graphs are based on real data. Since the radon and radon decay product concentrations are variable, it means that in practice, you can have situations where there is high radon concentrations and low decay product concentrations, and therefore low doses. But on the other hand, you might have low-ish radon concentrations and high radon decay product concentrations, and therefore relatively high doses. Therefore, if you use radon measurements to assess impact, it's important to work out what the appropriate equilibrium factor is, and therefore what monitoring you need to do. Okay, so let's have a quick look at radon 222, commonly known as Thoron. If you spend your life working with radon and then you shift to Thoron, it can really mess with your head. You've got to think about radon as a relatively, as a radionuclide with a longish half-life and short half-life decay products, whereas Thoron has a very short half-life and longer decay product half-lives. It was previously thought to be inconsequential due to its very short half-life. However, the Thoron concentration can be very, very variable and very different over time and distance. The key feature, the key reason Thoron may be potentially problematic is it's a short half-life. What that means, it has a fairly high generation rate. So you don't need much of it to produce activity. Remember that the radionuclide grows in with its own half-life. Another feature is that the concentration is highly dependent as distance from the source. There's been some work done by Shinji Tokonami out of Japan, where they measure radon concentration as a distance from a wall. The wall contains thorium-232, so you're able to measure that, and it drops off very quickly. The other issue with thoron is that it potentially interferes with radon measurements. Now, newer detectors are able to discriminate, so it's important just to, as I said before, think about what you want to measure. Thoron is not generally a concern in industries except where there might be high thorium or higher thorium, for example, mineral sands operations or rare earth projects where thorium is elevated naturally. For dose assessment, an approach is it's usually recommended that that you don't always measure thoron to determine dose. The most important thing to measure is the decay products. Thoron can be misleading if you're using that for the assessment of dose. So let's have a quick look at the equilibrium factor for thoron. If the thoron concentration is being used to assess dose, and I mentioned earlier that you may need to do that for modelling purposes where you don't have any measured data, then you can use the thoron with an equilibrium factor to give you an assessment of what the decay product concentrations are. And here's the equation when the equilibrium factor is 1 becquerel per cubic metre of, sorry, that shouldn't be Rn, that should be Tn as thoron, equals 7.56 by 10 to the minus 5 millijoules per cubic metre. Now remember that the equilibrium factor for radon was about 0.4 or 0.6 or something like that. But the recommended equilibrium factor for thoron is in fact 0.02. And usually when you look through the literature at monitored results or measured results, it can be a lot lower. And I've seen 0.008 through to 0.07 in the literature. And again, this is one of the reasons that we don't recommend thoron concentrations be used to assess dose in planned exposure situations or in situations where you can actually do thoron decay product measurements. It's better to do the thoron decay product measurements. Here's some graphs of some actual data. On the left, we've got thoron measurements. These are, I think, hourly measurements, and we've also got some thoron decay product measurements. And on the right there is a real-time graph of the changing equilibrium factor. Now, what does it say? It says it's quite variable. If we're looking at exposure, what you would tend to do is average over that exposure period what the equilibrium factor is, and that would give you an indication of what the exposure conditions were like. So one of the questions is, why are we measuring radon when we seem to have these problems with equilibrium factors and variability? Well, the reason we do it is because it's simple, easier, and basically cheaper. And what that means is you can do a lot more radon sampling generally for what you might do with radon decay product monitoring. Now that's changing, of course, with time as technology catches up. But basically, you can get a lot of passive monitors out, which give you a fairly good spread of what the radon concentration averages are. And if we use, of course, we have to know or assume an equilibrium factor in order to assess a dose from that. It can also, if we assume 0.4, it's usually adequate for buildings, but it can be quite different in underground mines. It can be, if you've got high ventilation rate, then the equilibrium factors for radon may be quite lower, a lot lower. I just want to say a few words on one of the bugbears of radon, which is the fact that we have a range of dose factors. And I don't want to say anything other than here they are. And again, this is potentially another talk in itself. you can, even as an experienced practitioner, you can look at that and go, wow, which one do I use? When do I use it? How do I use it? What are the situations I can use it? Should I use equilibrium factor or should I not? And it can cause endless headaches in practice. So ARPS has recently put new dose factors, including dose factors for radon and Thoron, onto their website as well. The International Framework for Radiation, so I'm going to shift now from talking about the details on radon to talking more about the guide, which was the intent of the talk. So hopefully I've got some time left up. Our international... Okay, thanks, mate. The International Framework for Radiation Protection is really, really good. It's really robust. You know, we have UNSCEAR providing the scientific basis for radiation protection. We have ICRP providing the philosophical basis for radiation protection. However, they do sometimes dip down into science and probably do it a little bit too often. Brackets. IAEA develops the standards and guidance, and that's usually a collaborative process where they bring people together from all over the world to develop the standards. And then in Australia, we have ARPS and the national authorities ARPS is the national authority who reviews and endorses the international guidelines. Oops, sorry. So understanding what is happening at the IAE level provides a perspective on what is likely to happen in Australia. And a really important point is that we need to constantly make sure that the standards being developed overseas are appropriate for Australia. And you will remember that for radon, we had quite a low average concentration compared to the rest of the world. So if standards are being developed, for example, in another country or in another continent, we really need to make sure that those standards are not, for example, Eurocentric, and properly take into account the Australian situation. So let me quickly talk about radon in workplaces, the document. A drafting committee was formed and met early in 2020, just before the COVID restrictions hit. The members of the group are on the right there, and I was fortunate to be nominated as a member from Australia, which was good. We met many occasions online to finalise the document. It was released by the IAEA for member state comments, and comments were incorporated. Consultation has ended, and I understand that it's in its final stages of development, so it's coming. The document did not provide any comment on dose factors apart from providing the table of how many there are. However, the document does note that the final decision on dose factors is a national decision. It was recognised to be quite a sensitive document, mainly because of the issue around dose factors, and it was unclear where assessments should occur, particularly in relation to planned and existing exposure situations, and I'll talk a bit more about this in a minute. The safety guide was based on GSR Part 3, the General Safety Requirement Part 3 of the IAEA, but the problem was there is varied implementation of GSR Part 3 around the world, and in some places it's just ignored. And similarly, as I mentioned before, reference levels, which are the levels above which you need to do something, need to be implemented, but again, they're different around the world in some places. But even some things surprised me in the drafting process that I didn't know about. The IAEA GSR Part 3 requirement is that for all planned exposure situations, you need to take into account the exposure and dose from radon. And this is not usually done for some industries. For example, the nuclear industry or medical facilities, medical operations, planned medical operations don't really think about radon that much, I would think. The other interesting thing is background subtraction of radon is not endorsed by the IAEA. And this sort of was a bit of a shock, because when we talk about an industry perspective, we talk about the increment that the industry contributes. However, the IAEA talk about the total exposure as a result of being at work. This caused some heated debate in the working group, and you may have noticed that there was a colleague from Japan on the group who was from the nuclear industry and was very, very vocal on it. In the end, the final outcome was that the document said put your hands up in the air and say it's up to the national authority to decide on both matters. So just quickly, the scope of DS519, as it's called, radon in workplaces. The objectives were primarily to, the objectives were to provide practical advice for planned and existing exposure situations, which I'll talk about in a minute. The scope included radon in workplaces and also some reference to Thoron. It considered the responsibilities of government, regulators, employers, employees, and service providers, and all types of workplaces, and protection for public who might come into a workplace. The document's quite straightforward, and here's the structure. I won't go through it in any detail, apart from saying that there's a framework for protection of workers in existing exposure situations and a framework for protection of workers in planned exposure situations. Important, quite important, and I'll talk about that now. Exposure, yes. So just on existing and planned exposure situations, this is where some of the big problems occurred in the document, in the writing of it. So we know that a planned exposure situation is when you get exposure from something that's obviously planned or a planned activity, whereas existing exposure occurs before a decision is made to take control from existing levels. And in some countries, norm operations, for example, are considered to be existing exposure situations. These differentiations provide a bit of a problem because the requirements for a planned exposure situation and the requirements for an existing exposure situation are different. And this causes quite a lot of confusion. Basically, for a planned exposure situation, the requirement is to keep the dose below the dose level and the dose constraint. However, for an existing situation, existing exposure situation, the requirement is to keep the radon levels or the exposures below the reference levels. And if the radon levels are above a reference level, then there's a requirement to optimize and get the levels below the reference level. Now, interestingly, there might be situations where you can't get the levels below the reference levels. So what do you do in those situations? And I'll come to that in a minute. But essentially, don't worry about the detail here. The point is that in general, for planned exposure situations and existing exposure situations, the differentiation is usually the activity concentration, another factor, which is usually a becquerel per gram or not. So on the left-hand side, if you exceed a becquerel per gram, then generally you end up as a planned exposure situation. And a planned exposure situation means you have to have a radiation management plan, etc., and ensure that workers don't exceed the dose limits. If it's less than a becquerel per gram, then essentially it's an exposure situation. And the requirements for that are essentially reference levels. In Australia, we use 1 becquerel per gram for industry as being a planned exposure situation. Now, I'm not talking about medical here, and I apologise for that. This is mainly in relation to industrial applications and industrial uses. But in Australia, ARPS has published the existing exposure document, and sets the reference level for workplaces of 1,000 per cubic metre. General exposure to workers are not considered to be occupational exposures unless they're part of their duty. It provides a guide for radiation protection, and workers are treated as occupationally exposed if reference levels are still exceeded. So there's a slight variation on the thinking in this. There are two main issues I'd like to describe. They may not be new because they already existed in GSR Part 3. The issues come to light and are amplified when we talk about radon, mainly because natural background levels of radon can vary significantly with place and time. So the first situation is the one that I alluded to earlier, which is the requirements for planned and existing exposures are quite different. But there's a grey area in the middle. It's those workplaces where you can't get the radon concentrations below the reference level. And for example, if we reflect back on that graph of average radon concentrations in the mines, the underground mines, there are a couple above the reference level. So if despite the additional ventilation, those levels could not be reduced, then what do you do? And the other thing is, when is the application of the radon requirements applicable? What is a workplace? It's quite difficult. Is it a place where, as I mentioned earlier on, exposure at work or exposure from work? There are questions that remained at the end of this document. And that's when the planned and existing exposure requirements may or may not apply. So if we quickly look at the difference between planned exposure situations and existing exposure situations for exposure, for occupational exposure. On the left, we've got existing exposure situations, again, based on reference level. What do you have to do? Reduce radon concentration and optimise. And your assessment method is the radon concentration. However, for planned exposure situations, you've got to ensure the dose limits are complied with. So you have to calculate a dose. You have to calculate a dose. You don't worry about the radon concentrations, you calculate a dose. And then there are various actions required. So as I noted, you'll note here that the reference level recommended by the IAEA in a workplace was 1,000. However, many countries have already mandated lower levels for workplaces between 200 and 400 becquerels per cubic metre. Interesting to note that if you're exposed to 200 becks per cubic metre for 2,000 hours a year at work using a standard equilibrium factor, then you might end up with 4 or 5 millisieverts. So for industries that have not taken into account radon before, then this is potentially interesting. Now, the situation that I mentioned before, what happens in between? What happens if you get existing exposure situations where you can't reduce the reference level below 1,000 or can't reduce the levels below the reference level? And of course, GSR Part 3 has a solution. Don't worry about the detail, but essentially it says that if you are an existing exposure situation and you can't reduce the radon below the reference level, then some of the requirements of the planned exposure situation apply. So it's not clear. So what you end up having is some of the requirements of planned exposure being used in the regulatory system for those particular situations. And you end up with a situation where you might have non-radiation workplaces becoming subject to planned exposure situation requirements. For example, hotels, car parks, schools, caves, cheese growing in caves and things like that may be subject to planned exposure situation requirements. And that's quite a significant shift in the way people think about how they manage their workplace safety. And here are some of the examples that we put into the document. Obviously, industries with noise, below ground workplaces, basements, mines, tunnels, galleries, tourist caves, fish hatcheries, etc. So all of these are potentially workplaces that could be subject to planned exposure situation requirements and dose assessment. So essentially, GSR did provide this interim solution, and it was we toyed with the term. It was either soft planned exposure situation or hard existing exposure situation requirements. But essentially, for those that cannot reduce below the reference level, there is a requirement to do some of the requirements of a planned exposure situation. And let me give you a quick example. Consider a planned exposure situation that's not measured radon before. So radon's not usually considered. However, radon is not incorporated into the assessment for worker doses. And an example here is you might have a workplace in an area with naturally elevated radon concentrations. So the person might be subject to 200 becquerels per cubic metre at home, goes to work, it's 200 becquerels per cubic, or let's say it's 300 and the reference level is 200, then at the workplace, the radon concentrations need to be reduced to the reference level. Otherwise, it becomes a planned exposure situation. And interestingly, the concept of it's not because they're at work does not hold. IAEA recommend that the background be included in the total dose when someone's at work. And interestingly, the reply from the IAEA on this is that the resolution is for the national government to decide, which seems to be what happens most of the time. Okay, let me try and bring together, and it's covered a lot of ground here, but let me bring together some key points here. And I have two sets of observations. Firstly, all workplaces really need to understand their radon exposures, full stop. And to do that requires investment in monitoring. Radon concentrations above the national reference level require reduction. So there is a requirement to get them below the reference level. Radon concentrations in workplaces below the national reference level still require some optimization. So it's a bit like the ALARA approach, which says, just because I'm below the limit doesn't mean that everything's okay. We still need to think about ALARA. And as noted, if we cannot reduce below the reference level, then some of the planned exposure situations requirements apply. For example, dose assessment or the development of a radiation protection plan. And my second set of sort of observations is that there are many, many international standards, even though they might only be applicable even though they might be developed or applicable in Europe, we still have to be careful about the development of international standards and their adoption in Australia. So involvement in the development of the standards is very important to ensure that we're able to apply those standards properly and not to the detriment of the country in Australia. I usually finish up with one slide, and it's my please keep risks in perspective slide. The idea behind this is that we can get lost in the weeds when we talk about radon and equilibrium factors and Thoron and half-lives, but it's always important to understand that radon is only one of a number of hazards in the workplace, as is radiation, and all need to be controlled. And I think that's where I'll leave it, if I may. Thank you very much.